Hash functions. I actually think that this is the most important lecture, not because I'm doing it. And you know, you had before we had, yeah. But it really does underpin a lot of what we do in all of crypto, and how we use these systems. And so, yeah, I think it's, yeah. Cool, let's go. So, hash functions. So, this concept of IDing. So, we have data and we want to identify it as something specific. And we want that representation of this piece of data to be binding to it, so that we know that this one thing that we get refers to the data. Like, this is kind of our goal here a little bit. It's one of the goals actually, but it's we'll talk about the different properties of them. But yeah, we want a succinct is another key word there. A succinct representation of data, and we'll see how we do that. Okay, some properties. So, hash function properties. Very just, you know, kind of. So, they should accept an unbounded size input. Okay, that's one of them. They should map to a bounded output. Okay, so something of size 100 goes in, it comes out to size 32 every time, as an example. Be fast to compute. We heard this in the introduction. Fast meaning not O of n, O of log n, it depends what n means. But in general, we're just thinking we want this thing to operate in practical, quick terms. Be computable strictly one way. So we talked about this idea of a one-way function. So normally, let's just think algebra, right? I have this f of x. I need to get the inverse of that. We can do that, right? Generally. We don't want that necessarily in this context. We just, yeah, we want going the other way to be very, very hard. It should resist pre-image attacks. So you control it. We're going to see an example of this too. But say an attacker controls one input. We want, so say the attacker has the words blockchain and they want to find a value which hashes directly to that. We don't want that. We don't want that to be easy. Again, we'll see an example of that. Second pre-image resistance. So say I have an input and I have an output, you know, blockchain, and I know what its input is. I want to be able to not find another input which maps to that output. So, yeah. So yeah, attacker has an input and output, and can find another input which maps to the same output. We don't want this. Want this one-to-one property. And more generally, this idea that we can't easily find collisions in the input space. So again, we have this function, something goes in, that's unbounded, it's whatever, and we get out this output that's fixed size. We don't want to be able to just search the input space and find two of them that map to the same value. Again, that's bad. We don't want that. That's a collision. Okay. Oh, we got a question. Number 1 of 4. I would just take that as being the input. Sorry, yeah. I would think of it in terms of, you know, it's just more of a math term, but we can, yeah. But I would just think of it as you have the output of the hash function and the pre-image coming as the input kind of. kind of, don't get too, yeah. Yeah, I mean, it's more mathy definition than that, but essentially. The input. Pre-image. So the image being, yeah. We're not going to go that math. Let's just say output and input. But it's here for, you know, we'll talk more about it. Okay. Here's a hash function API. I remember when Gav was teaching this, he was very adamant on this, you know, don't be scared. We talk about these things, but they're just, if you're a programmer, they're just something you call, right? It's a function. So what does it look like? So you have just some byte array. We don't know the length. It's whatever. And we get this fixed length 32 byte array output. Yeah. Typical one. Okay, so as we can see, so we have this short input, just hello, and then we have the whole Harry Potter series, but you get the same size out. I guess just kind of reiterating. So I guess just as maybe a little precursor, anybody see a useful property in that?
The size of the input.
This gentleman?
Cannot guess the size of the input based on the output.
Oh yeah, Mike. That's right. Let's just go one more. You had a good. I'll go to you. I think I don't know who had their hand up first, but I'll go to you. And we have 2 questions after you. Yeah. Oh no, but this gentleman.
Oh, okay.
And then you, Mark.
Hello.
Marcos. Yes.
Luke, my name is Luke.
Luke. Hi, Luke.
You cannot guess the size of the input based on the output.
That's nice. Yeah, that's pretty nice.
I had to pull it on this, but yeah, I just want to at least give a use case for something like this. So hash functions would be useful in the case of like verifying, like let's say an application, for example, you know, making sure that there's no sort of like backdoor.
No, I don't
exploit.
mean generally hash functions usefulness, which you're going the right direction. I just mean this particular property of having the same size input mapped to the same size output.
Okay.
Or, sorry, different size inputs mapping to the same size output, yeah.
Yeah, I mean, that's what, I guess no comment on that in regards to that sort of like response more or less, but yeah, that's what I was wanting to respond with in regards to checking the integrity of actual like piece of string more or less, so yeah.
Okay. And then one more and then we move on, I promise. Taking 4 per slide. Sorry.
Hi.
I'm going to be precise about it. You can ask it on the next slide. Yeah.
It's Mario.
Yeah.
I believe there is a value on indexing. It is more easy to index a value when there is the same format.
Oh, okay, yeah. I mean,
Map search goes directly to.
yeah. I mean, the which that kind of plays into it is like this content-based indexing, or you know, you can take some large thing and succinctly represent it, right? It doesn't matter the size. And so in computing, that's kind of nice, right? You can represent some data, doesn't matter the size, all with the same size. So it's quick. All right, I'm going to go to the next one. And don't worry, plenty of time for questions, not too much time though. Okay, input sensitivity. So this is a property, and this is even when they benchmark them, they have to meet these guarantees to be classified as certain security classifications, and we'll talk about more exactly what they are. But changing even 1 bit of a hash function completely scrambles the output, right? So here we have the hash of hello, and we have the hash of help. And these, as you know, in the alphabet come, I was even confused about this, but yes, we're changing a character, which is technically a byte, right? But these are right next to each other in the alphabet. So you're going from, I think, 59 to 60, something like this. And so you can see that these hashes, they look nothing alike. So it is sensitivity that just the smallest change. And so if we go back to the addresses thing, remember that when we're talking about hard derivations, like we just add in Polkadot or whatever on the thing and it completely changed the output. So input sensitivity is something that's important. Okay. Oh, yeah. Haven't heard from this person. Introduce yourself. Oh.
Sorry. Hi, I'm Carla. Didn't you say before that even if you did hello again, it would be a different hash?
No.
That would always be the same.
Yes.
But if you do it in terms of the numeric,
Oh, mnemonic.
and
Yeah.
then it's a different. Even
Oh,
though
it's even in your
even though
native
it's the
speaker. You're
same
struggling.
words.
Yeah. So the in terms of the mnemonics, we were changing some stuff. So the same one. This is one of the properties is they're deterministic. So the same input gives the same output. In the case of the mnemonic, that's why if you re-put back in your seed phrase and you lost it or whatever, or not lost it, but maybe you wanted to derive the secret again, you would just, the same seed phrase would get you the same secret. That's because this property.
But the different,
Of
the
the
different
deterministic.
accounts, the different accounts under it.
Oh no,
They're
that.
hashed. Isn't that part of a hash function?
So the different, yeah, in the derived accounts thing, which was that we would add in new things. So say this was our seed, our mnemonic. In the derived accounts, we were like adding something on it.
Oh, okay, like the / substrate.
Yeah, right.
Okay.
And that completely changes it because
Yes.
look, even one character completely changes it.
Okay, thank you.
Yep. Good. We will continue. Okay, so there's some demos of hashing a message. I think that I maybe would like to do this at the end. Yeah, I think I'll do it at the end. Yeah, I'll do it at the end. We just go through it all. Okay. Speed. So some hash functions are designed to be slow. Does anybody have an idea of why you would want the hash function to kind of be intentionally slow? All right, I don't know whose hand went up first. I'm going to choose this person and then that guy in the back. Yeah, but maybe he answers it and then it's right.
I guess it's to guard from some brute force attacks.
Yeah,
So they need a lot of computation power to brute force to try and error to find the content
Yeah.
before hashing.
yeah. So if you were trying to, this idea of brute forcing, which is I try all the combinations, and it involved something that had some slow computation in there, if that was made slower, then that brute force time has to go up, right? So anyways, just there it is. So like password hashing. But for what we use them for, we want them to generally be fast to compute because we like the succinctness property, amongst other things to do with, especially with signing signatures verification. Okay, here's some famous hash algorithms. So I guess we talk about the difference between cryptographically secure and not, but some of them are and some of them aren't. Does anyone know which one Bitcoin uses for proof of work? I don't know, I'm choosing Bitcoin. Jeff hates Bitcoin.
Here. SHA.
SHA, 256. Yeah. We use this Blake 2 a lot. And depends your application. Like for what I'm working on, I use this Kitchak or Kickhack or however you want to say it. Ethereum uses Kickhack a lot, right? They use, yeah. So yeah, some different ones. Then you have some non-cryptographic ones. We'll talk about why you'd want that. Maybe you can even see a little bit. XX hash 64 is 20 times faster than the Blake 2. Yeah, speed is sometimes the trade-off that you make. Yeah, this time. Mauricio.
Yeah, Mauricio.
Yeah.
Yes, so I was asking, okay, there's cryptographic hashing and non-cryptographic hashing. And the difference is one is not using cryptographic one is not using cryptographic primitives. So what is, okay, are we going to go into depth as in their difference and their security guarantees in terms of if it is non-cryptographic, what does it mean, like in terms of its
What's it used for?
no using for.
We're not
but
going to go into the details of the hash algorithm,
Okay.
but we could talk about those offline. Okay. Hash functions in blockchains. Okay, so, I guess I gave away the answer, or I guess we knew the answer there. So we do use RipMD 160 and Bitcoin as well, Ethereum Kekak, but they support some other ones. Again, we use this Blake 2 and the XX hash, depending on if we want cryptographic or not, in Polkadot and Substrate, but we have the ability, where we put this here, wherever we put this, probably Gavin put this here, that we support many other ones though through these things we call host calls, which we will talk about later in Substrate. You will use them if you're on the dev track. Yeah, so different kinds of hashing algorithms with different uses. So we have some benchmarks. So Blake 2, but SHA-1 is not cryptographic, right? SHA-1 got broken, like yeah, okay. So we have Blake 2B we use a lot, but you can kind of just see what are the speeds, why we chose it initially. I don't know like what's the latest on this, but it's important to look at speed of hash functions again because it's tied to so much in the system, especially when we're processing signatures for keys and transfers. So they are important. There's also, if you look at the notes for the slides, you'll see a reference in there. You can kind of look at the different hashing algorithms, the cryptographic ones. There is, I guess, yeah, here. We've got Blake 2 there, and this XXH64, which is, I guess, the really, really quick one. What else we got here? Spooky hash, nice. This is, I guess, this is for any hash nerd who just loves hash functions. They're really important though. So just giving you an idea of just kind of the speed and how they're benchmarked. And this on the end tells you whether they're cryptographic or not. Yeah, down here, SHA-1 was cryptographic, but it got broken. Do we have the mic in the middle section? Am I missing? Did anyone ask questions over there? No. I still care about you people. Over there and over there. I'm not looking at you guys. So.
Hi, Daniel here.
Hey.
What does it mean to be cryptographic?
Yeah, we're going to talk about that. But basically, in some contexts, you don't care if some of the properties when I said about these resisting attacks, resisting pre-image attacks and stuff like that. Some of the properties, there's different uses of hash functions. And in some cases, you want the properties to be enforced very, very tightly because that allows it to be safe. But in other cases, you don't care as much, and you can use hash functions for other useful things. That if one of the properties is broken, it doesn't kill your system, basically. Usually those are the fast ones. We'll do one more, yeah.
Can I have the microphone? So you don't have to like go really in depth with this question. It's more so just a lot of discussion based, but for context. A couple weeks ago, I saw a tweet from Troy Hunt announcing that a site got hacked as usual, and the site mainly used SHA-1 passwords. SHA-1 to encrypt passwords. Why exactly and how exactly did SHA-1 get cracked, more or less, or got broken?
I don't know, actually. I'd have to. I don't know the history.
Oh, okay. I was just wondering.
Yeah. But yeah, we should search that. I'm interested.
Yeah.
Cool. I will continue. Oh, one more. I haven't heard from this. We haven't heard from him.
My name is Mukhtar. Can you please comment the columns, like the width? Is it output, small data velocity, quality? Just
okay.
Thank you.
Are you familiar with what bandwidth is? Or are you on the dev track or the founder track?
I'm on the dev track,
okay.
And I just don't want to guess because I
don't know what quality is. That was an interesting quality. Like just a 10. Like there's one that's a 10 and one that's a 5 and a 9. I don't know what the quality score comes from. I do, okay, so data velocity, that's some measurement of, I guess, bandwidth. I have to go check what exactly velocity is. Width is just the bit width, right? Yeah.
So is it like the size of the output? 256?
It's a 256 bit output? Yeah, 32 bytes, right? Yeah.
Thank you.
Okay, cool. Okay, so we were kind of hinting at this, non-cryptographic hash functions. Yeah, well, what's the use, right? They provide weaker guarantees in exchange for being quicker. And the important thing is to know that when you know that the input is not malicious, and you think like, okay, what does it mean for the input to be malicious? So again, we think of this as like a theme, that if the user can control it, it can be potentially malicious. Nice and bold there. If you are doubtful who will control the input to the hash function, then just use the cryptographic hash function. But if it's user controlled again, then it's a user is basically an attacker in our world, then it's dangerous to let them control a weak hash function. They can really exploit the system that way. But if it's system controlled, then by all means, use a non-cryptographic. One way. So we talked about one way. So given a hash, it should be difficult to find an input value, again this pre-image, that would produce the given hash. So we say h of x is being the hash, and x being the input there. So, and when we say difficult, we mean really, really, really hard to compute. So like years and years and years of trying. Yes, we will talk about some of the applications of this. So we will sometimes add just kind of some random bytes to the pre-images to prevent guesses based on context. So if you're, I guess this is coming later, I have a slide for this. If you're hashing some, let's say, English saying, that's very common, right? If I'm able to see some, well, I guess, you know, whatever language you speak, if you're able to see some of the context, and you're able to, you know, say it's a popular saying, then it's kind of easy to guess what the rest of it is, right? So you want to avoid this kind of context-based guessing of the preimage. So that's why we use randomness a lot of times when we throw stuff into hash functions, because the randomness helps avoid some kind of context-based breaking the one-wayness. Oh, everyone's tired. Okay, second preimage tags. So, like I said, given the hash and the preimage, it should be difficult to find another preimage that would produce the same hash. We want the one-to-one again. So, in the context of when we were talking about the key stuff, right, it would be bad if someone knew another mnemonic, right, that would, this is kind of, we talked about like why hash more than once, right? It'd be kind of bad if, you know, we found another input that mapped to the same secret. That would be bad. That would mean that all of a sudden now I have another, I have your secret, I own your secret now, basically. That would be bad. So I think it's kind of obvious. If this is not obvious, you know, sure.
Yeah, Mauricio. So if a person can find another pre-image which leads to, if a person can find another pre-image when hash can equal to another pre-image being hashed, it means that hashing algorithm it's not collision free, right? It means like you can collide two pre-images together. So
there's no, everything is technically, it's not necessarily collision free. Like even the secure ones can have, there are collisions. It's just that it's hard to find them.
Okay, and how can you protect yourself from collision attacks?
Well, having a good hashing algorithm, that's a good one. But finding a second preimage, I mean, well, if it's a good hash function, it has it as basically a property. But we talked about the randomness stuff. I mean, that doesn't help you find a collision. But think about this. And the next slide is collision resistance, so maybe we can talk about it. But and especially in the programming exercise. But if there's a small input space, say that we can only hash, say, 10 numbers. How hard is it to find a collision, right?
Yeah.
Not so hard.
Yeah.
But if the input space is huge, like this is why the number that you pass in could be, you know, if the total input space is really, really big, then it's hard to find a collision because you need to choose from such a huge set of numbers.
Yeah.
So input size being big helps with, or the input range being big, helps with not finding collisions.
Okay.
Yeah. So since most signature and like digital signature schemes use hash functions, if you can get this, if you can execute this attack, then you can forge signatures. Basically, that's bad.
Shouldn't be the output size.
Huh?
Shouldn't it be the output size?
Mike, sorry, Mike. But I'm going to go after this question, not to the bathroom or anything. I'm just going to go to the next slide.
Yeah, you mentioned that the input size is the input range is the one that helps you prevent collisions. Shouldn't it be the output range?
No.
Like if you have, for example, like you said, 10
No,
numbers
because a
in the
collision is the. Let's just go to the next slide. There we go. Because a collision is that I find one number in the input and another number in the input, and they go to the same output hash.
Yeah, so if the output is like 10 numbers, like you said, it's going to be really easy to find two inputs that map to the same number. Because the
I
output
mean,
is really limited.
yeah, technically, but
I mean, I'm just not seeing the input relationship with the collision part of the...
yeah. I mean, the output size does need to be, it can't just be like, yeah, it can't just be 10 numbers, but the input size, if that's big, I mean, okay, yes, the output can't be like 10 as well. You need the input to be, input and output, to be honest.
Okay.
It can't be small. Like none of it
No,
can be
yeah,
small.
no,
If the set of numbers is small.
Maybe I'm thinking about it wrong, but I'm just thinking like, if you had the input be a number from 0 to 9, 10 numbers, you don't have really something
A big
that-
range, yeah. I mean, the output counts as well.
No. What I'm going to is if you have a number from 0 to 9 as the input, that's your limit. It shouldn't be, that shouldn't limit you to have more collisions because you can, the range of the output can be whatever. So you can have 0 mapped to 10,000, 1 mapped to whatever, and it shouldn't like give you more collisions to have a limited input. I mean, I see it on the output, but I don't see it on the input.
Yeah, you get the, okay. Oh, if the input size is small, then you get the pre-image. Both make it insecure.
Okay.
Yeah, but you're right. But yeah, I guess also this is, yeah. Both need to be sufficiently big. But we don't want the output size to be too huge, right? Because the whole point of this is that we want succinctness again. We want the thing to be fixed size. Good point, though. Thanks. Okay, so collision resistance, I think we kind of went through that a little bit. Should be difficult to find n, x, and y such that the hashes are equal. Let's see what we got here. Okay. I think we mentioned this. So again, in signatures, this is a big deal. Okay, the birthday problem. I was really excited for this slide. Oh, well, is that my, no, I don't have it open. So this is an interesting thing. I think a lot of people know this if they've taken some kind of probability or statistics, but it's true in this class, so I thought it's an interesting one. So we have this, with 23 people, there is a 6% chance that someone will be born on a specific date, if you just pick the date, but a 50% chance that 2 share a birthday, which is kind of just going to show that our intuition of probability, I don't know if that immediately you feel like that should be true, but in my brain it feels like it shouldn't be true. And this is just showing a distribution curve. And we have a class of 90, right? 94. And I mean, I don't know if that curve's accurate, but it says it like goes basically to 100. But we do have 2 people that share a birthday in this class. And it's coming up soon. So if you have a birthday coming up, oh, okay, yeah. We won't dox you, but we will bring a cake. Maybe not, okay. But I think that's cool, right? It's like we're talking about the birthday problem. It's like, that's not true. And then we have a sample size and then it's true. So it's kind of cool. So why is that the case? We have to compare each birthday with every other birthday, not with just one. We don't just pair, you don't just compare with one person. And so this number of possible hits or finding a match increases exponentially for more attempts. And I guess we're going to show some math here. We'll show some math of what it looks like. Congrats, whoever's got a birthday coming soon. Happy birthday. So there's this idea of the birthday attack. It is possible to find a collision of a hash function. We would just remove the, kind of go to the exponential notation of 2 to the n over 2 with, so the security of these, of the pre-image resistance is half of the bit space, right? So for a 256-bit output hash. So we talked about, yes, this 32 bytes, gives 2 to the 128 security. It's a pretty big number. Cool. Partial resistance. So we still want it to be difficult to partially find a substring of the hash output. So finding a collision or a second preimage. So let's go here. So Bitcoin proof of work, you can kind of think of it as a partial preimage attack. Does anybody kind of know anything about the Bitcoin proof of work and why that statement seems true? Your hand went up first, so that I saw. Am I not looking over here? Microphone.
Oh, sorry.
Hi, Luca. You have to find the hash that has a leading number of zeros, but you don't care for the rest.
Right. So this idea is that if you found the if you found the preimage for a hash, you would get all of the, you would know the whole preimage, I guess, that mapped to it, but you only care about getting, I don't know, some leading number of zeros. And this is how Bitcoin works to reward the miners, right? It's the problem that everybody's solving. This prefix suffix preimage attack resistance. Yeah, so there's this thing like this address spoofing, and it's typically used with these kind of you can create you don't want people to be able to like create an address which looks really close to the other address, and then people think they're interacting with, say, your account, and then it's actually somebody else's. So this is a kind of a common little trick. So having this prefix suffix preimage attack resistance is nice for kind of reducing this attack vector. Yeah, that's well said. Prefix collision resistance. Again, we're going to talk about the difference of why you would need a non-cryptographic or cryptographic. Okay, and here we are, selection. So I kind of made the point, if the attackers, the users, again, users being attackers, have control of the input, then you probably want a cryptographic hash function. But if it's something like, again, like an index or maybe keys for hash table or something like this, and it's just used for content addressing, for instance, then non-cryptographic is the way to go, because it'll be quicker to hash the keys to insert stuff into the table. Sure. Mike.
Hello.
Okay. That's okay. Can you please quickly give like a real world example of this?
All right. Can you please quickly give a real world example of each of these cases?
Okay, so
like the when we say in what case, in what use case do the attackers slash users might have? Yeah, we get it.
Yeah. So it's safe to use the non-cryptographic when people can't choose the input, i.e. like a system index, right? Like where the system's just going to assign an index to something. Like the user doesn't have influence over that. My next slide says applications.
Okay.
So I'm going to go to that one.
Higher level than that.
Yeah, yeah. Yeah. Cool. Applications. You're on the ball. Okay. So let's see which ones. If they didn't go to. There we go. Yeah. There we go. Okay. So confidentiality. So say you are going to post some public data. And do you want to, you're going to post some representation of some public data, but you want to keep that public data to yourself. You can hide what the actual public data is, and you can post a hash. So, you get this kind of confidentiality principle from that. Yeah, it leads up there, but we talk about commit reveal, and that's another use case, which I'll talk about in a second. So both cryptographic and non-cryptographic can work for this, because you're just like keeping the actual preimage hidden. Again, with the caveat that if the input space is large enough. Okay, bad example, and I wanted to talk about this one because we talked about context of the preimage and why that's important. So imagine we're playing some game. We're playing rock paper scissors, and say we're playing rock paper scissors, and every time that we're going to submit the moves, right? So in rock paper scissors. Right, if like I know exactly which one you're going to play and then I can play the other one in time, then I could easily game the system, right? So if we were just playing the game by submitting, say we had a 10-second window and we had 10-second window to basically submit our move, and you're going to post your move, you committed to it because it's too big, we're just going to do a hash. And every time it's rock, paper, and scissors, then because the hash function's deterministic, I'm going to know exactly which one it is because I can just figure it out. It's just three moves. So the other player doesn't need to undo the hash function. It just sees that there's just three different inputs, and because it's deterministic, you'll know what it is. Does anybody know how we would fix that? Okay, we just shouted it out. You could do that, but you basically some randomness source, right? Okay.
Yeah, I was going to say.
Do we have the mic? You do have a pretty loud voice, or you can speak, project loud, so it works. But well, let's be formal. Oh God, nice.
Yeah, sorry. I think someone already shot out the answer, but more or less, main example would be salted, more or less, for a given hash.
Salt? Like salt on food? No, I'm just kidding. Sometimes we call randomness salt.
Yeah.
Cool. Yeah.
Also, one other question. Well, at least just understanding more or less. I kind of relates to cybersecurity concepts, but more or less still on the same topic, more or less. Would rainbow tables be like an example of this, or like bad confidentiality, more or less?
Rainbow tables?
Yeah, rainbow tables.
Well, we can kind of show that it's not that good for, we'll get there. We'll get there. Okay, authenticity. So we're kind of, again, along the same path of like, what can we use this for in applications? So anyone can make a hash. So they don't provide any authenticity, right? So if I have, if I see a hash, can I really know who hashed it? Like, like anybody can run the function, right? So just from the output, I don't get any guarantees in that aspect. Integrity. So it does give you integrity because, again, we saw if just a single bit is changed or the data is changed in any way, then I get a different hash. So we get this integrity principle. And this, we talked about this in Saeed's intro, this non-repudiation. So again, on their own, they can't provide authenticity. And so we talked about these two kind of being linked. So depending on which order you go. So it can't provide this non-repudiation, but if you use it in another cryptographic primitive, so we use it in some signature stuff, then you, so basically the hash of some data provides the same non-repudiation as the data itself. So we'll see that at least in signatures. So again, the hash alone can't give me this authenticity thing. We have to use something else. Okay, content-derived indexing. So we talked, Ido said, okay, well, what can we do with this? So hash functions can be used to kind of get deterministic lookup keys for database. That's pretty useful. Yeah, it's pretty useful. They're used for that a lot. Data integrity checks. So, anybody use BitTorrent? Okay, good. One. Of course he does. Okay, good. So yeah, in BitTorrent, each file chunk that you're actually getting is a hash, is basically hash ID'd, so that you can basically know, like, okay, which chunk of the data do I actually need from the network? Does anyone know what a content address file is? Since we mentioned it here.
Yeah, Mauricio. So content based, okay, yeah, content address file. You just like hash the file, and the hash will be the key to the file it is. So it's kind of like used in decentralized file management, like cross network and other Filecoin. Like you're addressing the file based on the hash of its content.
Yeah. Basically, you have a file that has some data, and like the way that you get, like, I need this piece of data, then I know that this hash gets me this piece of data, basically. Yes. Cool. Is there another question? Everything good? Account abstractions. Yeah, public keys can be used to authorize actions by signing of instructions. Instructions, we also kind of, I guess this is a little blockchainy getting there, but instructions can be transactions. Yeah, I guess that's enough that I want to say on that. Public key representation. So we talked a little bit about ECDSA. We'll talk about it again in the signature thing, but not too much. So again, ECDSA produces this 33-byte public key. And so if we want to keep it in a 32-byte system, then we can use the hash function to actually mean that the public keys are actually hashed, and then that's the key, or that's the representation of the key. Just another use. Commitment schemes. So it's useful to commit to some information without storing or revealing it.
Hey, yes, sorry.
Sure, yeah.
I didn't understand the last slide.
This one.
Yes.
Okay, so we get a public key of size that has a size of 33 bytes. And one of the properties of hash functions was fixed size output. So, for instance, hash functions are used to represent ECDSA keys a lot of times. What part of that is confusing? Just so I understand. So the main thing is that the hash function allows you to get the fixed, the deterministic output. And so if you want something to be of certain byte length, like say addresses, then the hash function guarantees that you're going to have that size output.
I think the second sentence is that a system can map a plurality of key sizes to a fixed length.
Yeah.
A plurality of key sizes. I think this is what confuses.
Oh, okay. So say one ECDSA gives you a public key that's 33 bytes. Say an RSA key is whatever it is, huge. You could map those basically to the same. You can use the hash function to get a bunch of key sizes to that fixed thing.
Thanks.
Yeah. Anything else? Good. Okay, so commitment scheme. So it's often useful to commit to some information without storing or revealing it, which we kind of showed with maybe a rock, paper, scissors game. So any other applications someone could think of that would be useful with this kind of committing to something and then revealing it later? Since maybe we could talk about applications. You said an auction. A poker game? Yeah. Reading? Say reading? Breeding? Oh, betting. Yeah, betting. Yeah. Hey, gambling. Yeah. Yeah, Mike. We should mic it. Alicia's gonna get mad.
Hello?
Yeah. Band switch?
Hello? Hello? Yes. A more maybe relevant example, but also related to gambling, is that you could have Bitcoin, for example. Like you would be where there's basically a race that people need to compete for decrypting something. That could be it.
Compete for decrypting. Well, they're not competing to decrypt something.
Or rather, because there was a project that I worked on where there was a cycle of liquidity provisions, and then at the end of the cycle, basically, there's a random function that chooses who gets to provide the liquidity.
Okay, right. Example. And so you're saying that people committed.
The same idea as poker, that at the end something needs to be revealed, but
right. But you need to commit
that's more
to
interesting than poker.
Right. Okay.
That's it.
Hey, but I like poker. But yeah, I get it. Yeah. I'm gonna go here, then I'll go there, because applications are fun. Do we have the box? Oh, there we go. The cube, Polkadot cube.
I can think of any application that has different states and you store with the hash.
Can you put it a little closer?
Sorry. Any application that store a state, and then you could have a Merkle tree that hide completely all of the storing.
Okay. Well, we'll talk about Merkle trees in a little bit.
Everything that can be stored and you don't want to reveal can be hashed.
Okay, commit reveal. Well, okay. I was just looking for a little bit more of the application purpose, but I get what you're saying, and it's true.
Yeah.
Oh,
we do.
Yeah, that's right.
So think of prophecy, but Harry Potter. So Harry Potter goes.
I love Harry Potter.
Yep. So Harry Potter goes and says only he can get the prophecy revealed to him. So how does that work? So a genetic lock. The genetic lock means you put in something, but it will be revealed to the next generation. So wills.
Vince?
Wills. Will.
Oh, your will. You commit. Yep. Okay, right. Yeah. That would solve all those people like getting the grandma to sign the will over or whatever. That's good. Yeah, that happens. That might happen in my own family. Exactly. So committing to something without revealing it later, and then you can't go back on it, right? Because you've made some commitment to it, and maybe you haven't. So we use it a lot in blockchains. Spoiler alert. So basically, everybody said in one way or another, like a prediction market. So poker can kind of be thought of like that as well. But we only want to reveal the predictions after some point. Auctions, spoiler again, we talk about those a lot in the econ part, and a lot of spoilers. And we do some auction stuff with Polkadot currently. We might change it, but so pretty useful in terms of market stuff, prediction stuff. Another one is maybe users of a system want to discuss like some kind of proposal, right? So we take the hash of that proposal, we say, hey, we're going to vote on this. And then you don't actually have to store this huge proposal, right? You just need the hash of it, and you've committed to it, and this is the proposal that I'm working on, and someone can't just change it later, right? So it goes back to this principle that we're trying to like enforce again, is like not being able to change things later, right? Because this is an issue I think that we have in our world, right? Where we think that one thing is going to happen, then something gets changed behind the scenes, and that's bad. We want people to have to commit to things and not be able to renege on them and go back. Should not be able to, yes, basically what I was just saying. We don't want to be able to modify their predictions or their proposals, right? Oh, I actually voted for the other guy. Nope, you didn't. Cool. So this is like a general thing of commit reveal scheme. So you just share the hash of something, that's your commitment, and then you reveal that deed later. Again, it's like we said with the rock, paper, scissors, it's useful to add some randomness to make it so that the input's size is bigger. Okay, this is clearly a British person made this. And this is funny. So I predict this. Boris Johnson will resign. He was kind of unpopular when this slide was made. I don't know if he's still. I don't follow British politics very much. Hi, yeah. Politics always gets everyone excited too.
It's Carla. Just going back in the general concept of this hashing, in order to get the mapped data, can everyone get the underlying data, or can you add a layer of some sort of password? How does that work?
So can everyone, so in this case, like say we were predicting that, say we had a system that was taking in predictions of the date that Boris Johnson would resign. You would be able to, and they were just posting the hashes. There's only a finite amount of dates, right? Let's just say we're guessing for the month of July. So if we wanted to keep that a secret. So if you had all of this context and people were just submitting predictions on the date of the month July that they were betting on, then you would know what people's predictions were eventually, because there would just be 30 different ones, right? And you could just try each number in this set, and it would be easy to know which hash it was. So that would kind of break it. So the hash function, again, like if you have some piece of data, it produces a unique hash. But that's why if we do these things with predictions and stuff like that, we want to add in randomness. So like we have this prediction, but then we add on some randomness, and then, oops. And again, that makes the input size bigger.
Thank you. But what if you wanted someone to see it? So you were just using it as a directive to a big
Yeah. So
bunch of data.
that's again, this is like this idea that maybe I just want to. This is like I'm voting on a government proposal. We want to reveal what the hash is,
Yes.
and here's the proposal. You can verify that this is in fact the proposal. In that case, we're using the hash function just to give us succinctness. We're getting this ability for it to just be something quick and easy to vote on.
Yes, and how do they reverse it back to find what the underlying data is? Like, that's what the question.
Well, the thing is that you need to reveal what the data is, right? So if I say I'm voting on some proposal,
yes.
I put that into the hash function, I get a value. So I can just share with you the proposal and say, hey, I'm committing to this hash. And then if I give you the proposal, you can compute it yourself and you
Okay,
can
so it's
you can
only
verify.
after when they run the check through the
Yeah,
data.
you can verify.
Okay, thanks. Daniel.
That's the integrity property. Yep.
The hash itself doesn't prevent people from committing to a variety of different values in the past and then say in the future that they predicted something. For example, you could say, I predict that Boris will resign on the 1st, the 2nd, the 3rd, and all the available dates, and then I commit with all the hashes, and then in the future I just say, oh, I predicted something.
Well, if your system, that's like more of a system design thing, but if your system allowed people to submit multiple predictions per round, but I could basically say, well, here's the thing is that I could say, I'm running this prediction for X amount of time, and for each account, then yes, I'm going to take a prediction. But you're kind of getting more into like the Sybil problem, which is like I can be multiple accounts, right? The single person. But yeah, if you have a user-controlled system where I can verify that only you personally have submitted one value, then you can only submit one, right? But if you can be multiple accounts, and then yeah, we'll talk about this Sybil resistance thingy. Then you have an issue. Good. Okay. Okay, data identifier. So I talked about this a little bit. So we want to store some information in a place and reference it in another. So this, we use this hash as like an identifier, right? The state of a database. What is it at any one snapshot? We can commit to, like again, it's a unbounded input. We can get this fixed size thing. So we basically we have like a data ID, right? Yeah. I'm going to talk more about this, but we use this a lot. This is a nice way of committing to some piece of data. The proposal was one example, but we can kind of generalize that to be more of like the state of a database. Okay, so we have a lecture tomorrow, more on in the data structures realm, but we just give a little introduction. So we have pointer-based linked lists. So one thing about pointer-based linked lists, if you did computer science at all, hopefully you went over this. So you have a list, a collection, and you have a data item, and you know, in this one data item, it points to another one, right? It points to the previous. So you have some sequential, you know, something that has some kind of collection structure. The issue is that in a traditional linked list, you have that the pointers are independent from the data that they actually represent. So, meaning that you could have a list of data and it could be going in some sequence, but this pointer, basically you can change the data there, and down the line it doesn't really know, right? There's no commitment to the sequence in a way. So there's this idea of being tamper-proof, and so pointer-based linked lists are not tamper evident. So we use hash functions, and we have hash-based linked lists. So they make the reference to so the properties that it's helpful with the diagram, which I'm going to show on the next slide. But basically, we can use the hashes of the previous data items. Remember, we said that we have this data ID thing. So when we have when we formulate the pointer in a linked list, for instance, we can hash the previous thing, right? And so that means that in the pointer, it directly only references this one thing. So if I went back and I changed the one data item, then it would affect it down the line, right? Because the pointer is linked, it's committed to, it refers to something specific, an individual, something unique. Okay, Merkle trees. This is very important for your assignment. So, which you're going to love, this part. So, we have, we love trees in computer science. So we have this structure where we have a list of data items, and we want to have a single hash represent all of the data, right? So I kind of talked about committing to like the state of a database, which this will be repeated as we get more into blockchain and substrate and later things. So we have a list of data items. We could say it's a block, we could say it's a transaction, we could say it's whatever. Data 0 through 3 or 4 items. And we can kind of do multiple hashing to commit to all of the things in one single hash. So we could first hash data 0, we could then hash data 1, and then we could add those hashes together and hash that, and that gives you this. That's h of 0 plus h of 0 plus 1. And then we can do the same thing on the other side. So we hash data 2, we hash data 3, we add those together because, again, hashes are just numbers at the end of the day. And then we hash that, and that gives us this node over here. And then we can add it, we can do it, basically we can do this a bunch of times. And we can get one single root hash, which we call the state root, usually in blockchains, that represents all of the data inside of the tree. So we call this a vector. You're committing to a vector of values. And I guess I'll talk, I don't want to step too much on my other one. But I guess I'll just leave the picture up because my next one. So basically what that allows us to do is that we can formulate using just giving somebody having access to the root hash, we can create a proof that, say, data item 1 is in the tree. Could anybody think of which nodes we would need to pass to somebody in order for them to verify a proof that it's not that big of a proof, right? So if we wanted to prove data 1 to somebody else, do you know what we would need to give them in order for them to verify that proof? So what would the proof look like? No, it was first. I think he was first. Box mic thingy.
Ask them hash 0, 0 and hash 1. And I assume like they have the data so they can compute hash 0, 1 and they have the root
Good. Does everybody see that? Or if you don't see it, just... Okay, yeah. So let me repeat. So he said you need to pass hash 00, right? And then pass hash 1. And then they can recompute the root, right? So if they have the root, and I say data 1 is in there, that's what I need to hand over to the person for them to verify.
Yeah.
So I guess a question, why do I pass them only hash 1 and not... Can you, Mike?
Because hash one is a factor of hash 10 and hash 11. So any change to hash 10, hash 11 would be reflected in hash 1.
Perfect. Again, it's just showing that we know by the properties of the hash function that they couldn't have changed hash 10 or hash 11 because this already gives a commitment to both of them. There's a question over here. Mike.
What if the length of the vector is uneven?
We'll get to that. That'll be in your program. Basically, we just add. We add like some hash of something that's like empty, like the empty string, or it depends what your application is. But you just have like something that you hash at the end to get it to be even, generally. Okay. Yep. So Merkle tree is pretty important for the rest of this course, especially on the dev track. So we'll have more on that in the next hash-based data structures lesson.